Okay, so welcome to this next video in which we are discussing the phospholipase C beta family of enzymes. Okay, so we are currently in the process of discussing how we are going to activate phospholipase C beta enzymes through the activation of G protein coupled receptors, which will activate GQ/11 heterotrimeric G proteins. Okay, so we've just discussed all the different types of heterotrimeric G proteins. What I now want to discuss is the G protein cycle, and I'm going to do this in full generality before going specifically onto heterotrimeric G proteins of the GQ/11 type. Okay, so the G protein cycle then. The G protein cycle is the mechanism by which G protein coupled receptors are going to activate heterotrimeric G proteins. Okay, so let's just draw everything that we know at the moment and then we'll see what's going to happen. So we'll start off with our G protein coupled receptor here with its 7 membrane spanning alpha helices. The amino terminus is extracellularly and the carboxylic acid terminus is intracellularly. Okay, so here's our GPCR, our G protein coupled receptor. Then we've got our heterotrimeric G protein here, which is currently in the off state and therefore is currently assembled as a full heterotrimeric G protein. So here is our guanosine diphosphate bound to the alpha subunit here. Okay, and this will then be in a complex with a beta-gamma complex, which involves a beta subunit bound to a gamma subunit. Okay, and that gamma subunit also has a lipid moiety coming off it, which attaches it into the inner leaflet of the phospholipid bi there. Okay, so let's colour this in. Here's the beta subunit in blue. The alpha subunit once again we'll have in red here. Okay, and then finally the gamma subunit we'll have in green. Okay, right. So now let's say that the ligand for our G protein coupled receptor comes along and binds to the G protein coupled receptor. So in comes the ligand. This will trigger a conformational change in the G protein coupled receptor that will be translated down into a conformational change in these 3 intracellular loops down here, which I'll highlight in orange, the ICL1, the ICL2, and the ICL3. These will now make available a binding site for an alpha subunit of a heterotrimeric G protein. Now, every G protein coupled receptor will have certain alpha subunits which it likes to bind and then others which it doesn't like to bind. Okay, so it will bind to specific alpha subunits and therefore it will only bind to heterotrimeric G proteins which have that specific alpha subunit in. Now, it's not quite the case that they'll only bind to one alpha subunit, but they will have their favourites. So, for instance, some G protein coupled receptors will specifically activate alpha subunits that are G alpha I subunits, so either G alpha I1, G alpha I2, or G alpha I3. Okay, some G protein coupled receptors will only activate G alpha S subunits, things like that. So, all G protein coupled receptors will have their preferences for alpha subunits of heterotrimeric G proteins that they like to bind to. Okay, so what's going to happen is now our G protein coupled receptor is going to bind to the heterotrimeric G protein. Okay, so I will draw the G protein coupled receptor spun around 180 degrees so that I can get the carboxylic acid terminus out of the way. Okay, so I'm going to just spin it around 180 degrees. This is just going to make it easier to show the alpha subunit bound to the underside of our G protein coupled receptor. So here's our amino terminus, and now our carboxylic acid terminus is nicely out of the way now. Okay, and now I'm going to show the alpha subunit bound here, like so, to those 3 intracellular loops there. Ooh, and I'm going to struggle to get GDP in there. Okay, but there we go, there is GDP just squashed in there. Okay, and I'll colour this in once again in red. Okay, so here is the alpha subunit still currently in the off state. Okay, and it's bound now to these 3 intracellular loops here. Now, in order for the alpha subunit to bind to the 3 intracellular loops, it is absolutely essential that the alpha subunit has bound to it a beta-gamma complex. Okay, so although the beta-gamma complex isn't itself involved in binding to the free intracellular loops of the G protein-coupled receptor, i.e. it doesn't itself bind, it has to be bound to the alpha subunit in order for the alpha subunit to bind to those free intracellular loops of the G protein-coupled receptor. So if the alpha subunit didn't have a beta-gamma complex bound to it, it wouldn't be able to bind to the intracellular loops of our G protein-coupled receptor. Okay, so let's now colour in the beta subunit once again in blue, and the gamma subunit in green. Okay, and once again, of course, the gamma subunit will be attached to the inner leaflet of the phospholipid bilayer via this lipid moiety. Okay, and the alpha subunit still has its lipid moiety. Now, once the alpha subunit binds to the intracellular loops of the G protein-coupled receptor, like so, the effect of that is it allows the alpha subunit to release its guanosine diphosphate. Normally, the alpha subunit binds to that guanosine diphosphate extremely tightly, but once the alpha subunit binds to the intracellular loops, its hold on the guanosine diphosphate becomes much looser, so it releases it out into the cytoplasm much easier. And then what will happen is a molecule of GTP from the cytoplasm will come in and replace that guanosine diphosphate in that guanine nucleotide binding pocket of the alpha subunit here. Okay? Now, when GTP binds to the alpha subunit is now in the on state, so the alpha subunit will change conformation when the GTP binds, and this new alpha subunit conformation is no longer capable of binding to the beta-gamma complex. So what will happen is the beta-gamma complex will cleave away from the alpha subunit, and it will go off and scoot over here, basically. Okay, now once the beta-gamma complex is no longer bound to the alpha subunit, then the alpha subunit, as I said, is not capable of binding to the free intracellular loops of the G protein-coupled receptor anymore, so it will also cleave away from the G protein-coupled receptor. So let me show this here. Okay, so we've got the alpha subunit in the membrane, okay, here, bound to guanosine triphosphate, GTP here. Okay, and then we've also got the beta-gamma complex now free, hanging underneath the inner leaflet of the phospholipid bilayer. So here's the beta subunit and here's the gamma subunit. Okay, so let's colour these in. So we'll colour in the alpha subunit in red again. Okay, and then we'll colour in the beta and the gamma subunits in blue and green again. Okay, so beta's in blue, gamma is in green. Okay, right. So, now both of them will go off and have signaling roles. So for instance, let's draw some targets in the membrane. So here this can be a target for the alpha subunit of the heterotrimeric G protein now that it's in the on state. So it will go and bind to target 1 here, okay, which I'll colour in purple, and it will cause some downstream effect. Basically, it will interfere with the activity of target 1. Okay, now not only will the binding of the alpha subunit with GTP bound affect the activity of target 1, but also when the alpha subunit binds to target 1, what will happen is target 1 will also affect the activity of the alpha subunit. Okay, and we'll come back to this in a moment. In addition, the beta-gamma complex will also have targets. So over here, let's say this is target 2 over here. So the beta-gamma complex can also go and bind to targets that are within the membrane and affect their activity. Now coming back to this effect that target 1 has on the alpha subunit itself, basically, when the alpha subunit binds to target 1, it's going to affect the activity of target 1, but target 1 is also going to reciprocate. It's going to affect the activity of the alpha subunit. Now, the alpha subunit is actually an enzyme. It's actually a GTPase enzyme. Now, GTPase enzymes are enzymes that catalyze the hydrolysis of guanosine triphosphate into guanosine diphosphate, GDP, and also an inorganic phosphate molecule. Okay, so this reaction is catalyzed by GTPases. So, when target 1 activates the alpha subunit, it's going to activate this GTPase activity here, and the alpha subunit is now going to act on that GTP molecule that it's got bound there, and it's going to hydrolyze it into guanosine diphosphate and an inorganic phosphate. The inorganic phosphate will be released into the cytoplasm, whilst the guanosine diphosphate will remain bound to the alpha subunit. That means that the alpha subunit has been activated to turn itself off, basically. Okay, so what now will happen is once the alpha subunit is in the off state and has guanosine diphosphate bound to it rather than guanosine triphosphate, the alpha subunit will cleave away from its target, in this case target 1, so it will cleave off and go back into the membrane, okay? So it can no longer bind to its target once it's in the off state. Only the on state alpha subunit can bind to its target. Okay, the alpha subunit will then go running crying to the beta gamma complex and will snatch the beta gamma complex off its target and rebind it. Okay, so it will return to the inactive heterotrimeric G protein up here, and this is why it's called the G protein cycle. Okay, because we go through these cycles of activation and inactivation. Okay, right, so that's the G protein cycle in full generality. That works for all heterotrimeric G proteins and the general G protein coupled receptor. Let's now put some specifics on here. Okay, so we're now going to be working with a G protein coupled receptor that binds alpha subunits that are in the G alpha Q/11 family. Okay, so either G alpha Q, G alpha 11, G alpha 14, or G alpha 15/16. So we're only working now with G protein coupled receptors which couple through heterotrimeric G proteins with this sort of alpha subunit. Okay, now what examples are there of G protein coupled receptors which do indeed couple through heterotrimeric G proteins with an alpha subunit within this family of alpha subunits? Well, some famous examples would be the alpha 1 adrenoreceptor. Or in addition, you have the M1 and the M3 muscarinic receptors. They are good examples. And there are many other examples as well. Those are the adrenaline and muscarinic ones, but there are many other examples as well. Okay, so what we now want to see is what's the effect then of having an active alpha Q/11 alpha subunit. Okay, so the entire heterotrimeric G protein which has an alpha subunit in this family is going to be called a GQ/11 family heterotrimeric G protein, which just means that the alpha subunit is in this family of G alpha Q/11. So the G protein coupled receptor will activate the heterotrimeric G protein when its ligand binds to it. Then what will happen is the alpha subunit with GTP bound is going to go and stimulate targets, and the target that we are now interested in is going to be a phospholipase C enzyme of the beta form. So I will now remind you, phospholipase C enzymes of the beta form, we've discussed that when they're in their inactive state, they are continuously moving between this being in the cytoplasm and being bound to the underside of the phospholipid bilayer. The alpha subunits are going to bind to the form that is currently bound to the underside of the phospholipid bilayer. And by binding, it's going to stabilize that phospholipase C beta enzyme at the underside of the phospholipid bilayer. So let me draw this. Okay, so let's draw our phospholipase C enzyme once again. Okay, so remember we usually start with the carboxylic acid terminus here, and then we had that C-terminal domain that was extremely important in binding to the underside of the phospholipid bilayer, but we don't fully understand how it actually is binding yet. Okay, then after that we had a domain called the C2 domain, which was incredibly important in other phospholipase C family enzymes for binding to the phospholipid bilayer, but in the case of the phospholipase C beta enzymes is not terribly important. Okay, then we had our Tim-like barrel domain here, okay, which had the catalytic site at the center here. Okay, like so. and was split up into these two sides, the X domain and then the Y domain. Okay, and then you have that loop between the X and the Y domain, the XY linker, which I'll colour in vivid purple here, which sits in the catalytic site and is blocking the catalytic site from functioning at the moment. Okay, and we'll also draw out the XY domains in yellow here, we'll colour them in. Okay, so there we go. And then coming off, oh, and have I got the X and the Y domains wrong? I have got them the wrong way round. Let me just correct that. This one should be the Y domain and this one should be the X domain. So the Y one is the one towards the carboxylic acid terminus and the X one is towards the amino terminus. I got confused because I'm working from the carboxylic acid side to the amino side. So then coming off the X side, okay, here, you're then going to have these 4 EF hand domains, okay? So I'll draw 2 like so. And then I want to try and show the plextrin homology domain also bound to the inner leaflet of the phospholipid bilayer. So I'm going to stretch this out a little bit, put these 2 other EF hand domains here, and then we'll have this plextrin homology domain bound here, and then the amino terminus over here. Okay, right, so let's colour this all in. So we'll start with the plextrin homology domain here in turquoise. Okay, and that's involved in weakly binding to the phospholipid bilayer, so it contributes, but it's not terribly important. Okay, then you have these 4 EF hand domains which do not bind calcium, and we don't really know what these are actually doing. Okay, usually in other proteins such as calmodulin, EF hand domains are extremely important for binding calcium. Okay, so these are the EF hands. Okay, and this then currently is our inactive phospholipase C enzyme that is bound to the inner leaflet of the phospholipid bilayer. What's now going to happen is our alpha subunit, which is an alpha Q/11 subunit, which is in the on state, is going to come and bind to the C-terminal domain. So I don't quite know how I'm going to show this. Okay, I'll sort of try and squeeze it in here. Okay, so along comes our alpha subunit here, okay, which is of this alpha Q/11 family of alpha subunits, and which is in the on state and therefore has GTP bound. Okay, so this is an alpha Q/11 family alpha subunit. There's its lipid moiety still attaching it into the phospholipid bilayer, and this is going to come and bind to the C-terminal domain. Okay, and when it binds to the C-terminal domain, what it's going to trigger is a conformational change that will move the XY TIM-like barrel domain up here against the phospholipid bilayer. So this will move up and now be nicely opposed to the phospholipid bilayer. Okay, now when this happens, what is proposed to happen is the XY linker will move out of the catalytic core. Okay, and the reason this happens is that the XY linker contains a large number of acidic residues. Okay, now what's the significance of it containing a large number of acidic residues? Well, if I draw you an example of an acidic residue, a nice example of an acidic residue would be an aspartic acid residue. So I'll start with the core amino acid structure here, and then the R group of aspartic acid consists of a methylene group with then a carboxylic acid group coming off the side. Okay, so this is aspartic acid. Now, aspartic acid being an acid can donate a proton away into solution. Okay, so what can happen is this proton can be lost from this alcohol group here, leaving the oxygen with a negative charge. Okay, the molecule that you then have left over, which is the conjugate base of aspartic acid, is then called aspartate. Now, under physiological pH, many of the acidic amino acid residues, such as aspartic acid, but there are other examples as well, such as glutamic acid, they donate their protons away into solution and therefore exist as the conjugate base form, such as aspartate. And the conjugate base has a negative charge. So basically, if you've got a large number of acidic residues within this XY linker, some of them at any one time will have donated their protons away and therefore will have a negative charge. So basically, by saying you have a lot of acidic residues there, you are effectively saying that you have a lot of negative charge here. Okay, now when you move this XY domain so that it's facing right underneath the phospholipid bilayer. The reason the XY linker is thought to move out of the catalytic domain is that it will feel a repulsion from the heads of the phospholipids in the phospholipid monolayer. Okay, so remember, not the phospholipid monolayer, the phospholipid bilayer. Okay, so remember, the phospholipids in the phospholipid bilayer will all have phosphate groups near their heads, okay, well, as their heads, and these phosphate groups all have negative charge. Okay, so the underside of the phospholipid bilayer is negatively charged, so when you move this XY tin-like barrel up here, the XY linker will feel repulsion from these negatively charged phosphate groups of the phospholipids of the phospholipid bilayer, and it will be repelled as far away as possible, and that will mean that it comes out of the catalytic core of this XY tin-like barrel domain. Okay, and that then means that our tin-like barrel domain is going to be sitting nicely underneath the phospholipid bilayer. Okay, like so. So here it is, with its catalytic core now no longer obscured by the XY linker, which is out of the way here. Okay, so here's the XY linker now nicely out of the way. Okay, and now what will be able to happen is the PIP2 molecules, of which I'll draw one here, okay, or at least try this time to fit it in here. So here is a PIP2 molecule. The PIP2 molecules, which are within the phospholipid bilayer here, okay, like so, they will stick their heads into the catalytic core, which is here, of the XY tin-like barrel, and now the phospholipase C enzyme will be active and will be catalyzing the conversion of PIP2 molecules into diacylglycerol molecules and IP3 molecules. So that is the way that these alpha-Q subunits, or alpha-Q/11 subunits, are going to activate phospholipase C enzymes. They cause this change in conformation that moves the XY barrel nicely against the underside of the phospholipid bilayer. In addition, they also stabilize the entire enzyme at the inner leaflet of the phospholipid bilayer, so it's not as though it's now going to move into the cytoplasm. This interaction is now not going to break off, it's stabilized there. Okay, but at the same time, the binding of the alpha subunit to the C-terminal domain is going to activate the alpha subunit's intrinsic GTPase activity, okay, like I described earlier. And therefore, the alpha subunit is a time bomb, effectively. It's going to turn itself off after a while, and therefore, once it's turned itself off, it will cleave away. That will mean the XY barrel moves back away from the underside of the phospholipid bilayer. It can no longer catalyze the reaction, and also the phospholipase C enzyme of the beta type can now fall back into the cytoplasm. Okay, so the alpha subunit stabilizes the binding to the membrane and also causes this movement of the XY barrel so that it's now positioned nicely underneath the inner leaflet of the phospholipid bilayer, so that it can actually work on the PIP2 molecules in the inner leaflet of the phospholipid bilayer. Now, the final thing just to say is that once again, I'll stress that all of the alpha subunits within that G-alpha-Q/11 family can do this, and that generally they are better at doing it for the beta-1 and the beta-3 forms of phospholipase C beta than they are at doing it for beta-2 and beta-4. So they're better at activating phospholipase C beta-1 enzymes and phospholipase C beta-3 enzymes than they are at activating phospholipase C beta-2 and phospholipase C beta-4 enzymes. Okay, and that now concludes our discussion of phospholipase C enzymes of the beta family.